Hello, I'm going to talk to you about our implementation of shift field refinement in CCP4, and in particular the sheet bend software which we've used to do that. So, the software is designed to do refinement. It's a key step in the structure solution process, but it can be difficult, especially in the case of molecular replacement, when we may have significant differences between our molecular replacement model and the structure that we're trying to solve. For example, this loop or this helix here. So, how does refinement work? Well, we're familiar with looking at electron density maps calculated with our best phases, and we can see in some places where the model does not fit the electron density map. But if we're just interested in the errors, we can use the difference map, which shows where we have atoms which are not explained by the X-ray observations, or density which is required by the X-ray observations but has no atoms. So the refinement tries to minimize the features of the difference map, and in doing so produce the model which best explains the experimental observations. How does it do this? Well, we need to determine how to change each parameter of the model in order to reduce the features of the difference map. And we do this by calculating a gradient map. This is a gradient map in the y direction, so it shows positive features above all the atoms and negative below them. And where we see agreement between the gradient map and the difference map, that tells us that that parameter, the y coordinate in this case, needs to be increased in order to reduce the features of the difference map. So if we move all these atoms upwards a bit, we increase their y values, we will reduce the features of the difference map. Now, there are a couple of problems with this. Firstly, the difference map is the difference between two signals, so it is by definition very noisy. When we subtract one signal from another signal, where the signals are largely similar, then the differences are going to contain much greater contribution from the noise compared to the signal. The other problem is that the gradient maps are by definition very sharp. It's a fundamental property of gradient maps. So when we combine information from the sharp gradient maps and the noisy difference maps, we get results, we get parameter shifts, which are themselves very noisy. So that looks like the case on the left over here. Whilst there is a broad trend that the atoms need to be moved upwards, there's enough noise that individual atoms may be moving in any direction. And as a result, this tends to rip the model to shreds. And to avoid this, we need to introduce stereochemical restraints. So we have the experimental observations pulling the model to bits, and the restraints trying to hold it together in order to extract these general shifts, these large-scale motions to bring the structure into the right place. So that's a bit clumsy, and it does slow down the calculation and limits its radius of convergence. It's less good at finding these big domain motions that we want to pick out at the early stages of refinement. So the change we made is, instead of looking at the shifts to individual atoms, we look at the shifts over a whole region, and that takes out a lot of the noise. So we end up with big coordinated shifts which vary slowly over a whole region of the map. So that gives us the kind of shifts we want to see for these without needing stereochemical restraints at all. And that both makes the calculation faster, and it makes it better able to pick out these large domain shifts that we want to detect. So, how's this implemented? We've implemented it in software called sheet bend with an iterative approach, and we do typically 12 cycles of coordinate refinement, starting at 6 angstroms resolution and averaging over a very big region, and increasing the resolution stepwise to 3 angstroms when we can look at more detailed features. Now, shift field only does part of the calculation. It doesn't deal with things like detailed sidechain fitting, so we then do a conventional refinement in RefMac afterwards. So does it work? Well, we can compare using shift field versus not using shift field, in both cases followed by conventional refinement. And here's comparison of free R factors. Any cross below the line, shift field has done better. So we see there are a few cases where it's done worse. The majority, it's led to a very small improvement, but there are some cases where there were big domain motions that were not picked up by conventional refinement, where it can lead to R factor improvements of 5 or 10% or even more. There are other methods for addressing this problem. So, for example, jelly body refinement in RefMac. And if we do a comparison against that, we find that there are cases where jelly body does it better, and there are cases where shift field does better. But there are increasingly, for the most difficult cases, shift field can pick up these large domain shifts that lead to very large drops in free R factor. And here's one case where that happened. So here is the jelly body model in red. The blue model here is the shift field model, and the thin black lines are the deposited structure. So in this case, it has picked up a large shift of about 4 angstroms. The other feature of the calculation is that it is very fast, and that's partly due to the lack of restraints, the fact that we're not pulling the model in different directions, but primarily due to the fact we can work at much lower resolutions. So the shift field refinement is typically 4 to 20 times faster than conventional refinement, depending on unit cell volume, and 40 to 200 times the speed of jelly body refinement. So that makes it particularly amenable to large-scale screening calculations where we're doing lots and lots of molecular replacements. Now, this is implemented in some of the molecular replacement calculations in CCP4I2 and also in the Buccaneer pipeline, and we're going to implement it in CCP4 cloud model building through an upcoming model building pipeline called Modelcraft, which Paul Bond is developing. It's also been implemented to provide fast B-factor refinement in COOT, and there's also a standalone CCP4I2 task. Although you shouldn't really use this, it should really be used through a pipeline, but I will show you it just so you can see what kind of information it needs. So here's a demo. Don't do this, use it from within a pipeline. So I'm going to go to the refinement menu and pick fast preliminary refinement for atomic model coordinates, including at low resolution. So that's sheet bend. And we need some reflections. I'll pick these, a free R factor, and an atomic model, which I want to use an earlier one from here. And basic options, by default we run for 12 cycles, and we start at 6 angstroms and go to 3 angstroms at the end of the calculation. So those should be the defaults in future. And then we'll click run. The calculation should only take a few seconds. Obviously it does get slow with larger structures, but as you can see it was very quick. Now, it produces a table of R work and R free as a function of cycle. Beware that you cannot compare these from cycle to cycle because we're changing the resolution constantly. So these numbers aren't comparable from cycle to cycle. The only thing you can use them for is comparing 2 different runs which finish at the same resolution. Okay, so that's the program as it's implemented within current pipelines. We've also been doing some further work. One of the problems we found is that shift field refinement can lead to chain breaks when you run in enough cycles, even though it's trying to make big, smooth shifts to the model. And that's why we limit the calculation to 12 cycles. We would like to be able to run more cycles to pick out larger motions, but that tends to lead to more breaks in the chain as things gradually get more distorted, and these can be big enough that RefMac can't put them back together. So if we could restore conductivity, it would be possible to use more cycles and pick up bigger shifts. So to do that, we've implemented pseudo-regularization. And what we do here is we pick out 5 residue segments from the original chain and superimpose them on the shifted chain. And we do this for each overlapping 5 residue stretch in turn, and then blend these together to build a reconstructed shifted model. And this is very, very fast. It's essentially instantaneous, but it does fix all the breaks that can be introduced. So we can implement this in an iterative method. We do 12 cycles of XYZ refinement. We add an extra cycle of B value refinement, and then we do the pseudo-regularization. We do this 3 times, and then we go into RefMac. And comparing this to existing methods, jelly body and shift field refinement were broadly similar, very slight benefit to shift field when averaged over 452 cases, although the methods are complementary, sometimes one is better than the other. If we add pseudo-regularization, we tend to drop about another % in R factor. So that's quite a significant further improvement, especially given that that's concentrated in the subset of structures which have large domain shifts. A lot of them were well refined already, and they see no benefit. So the benefits can be quite significant. So what does that look like? So I will clone the job, and we will look at the basic options and then advanced options. To do this, we turn on pseudo-regularization by clicking this box. We do more cycles, and we'll turn on the extra isotropic B factor refinement step. Now, this isn't yet implemented in molecular replacement or model building pipelines because it's not quite as stable and mature as the existing calculation, but we'll be working towards that over the next couple of months. So that's all for now. People who've worked on this, John Aguirre, Paul Bond, and Stephen Metcalf in my group. We've had funding from BBSRC and from CCP4. And Scott Ho is also working on an implementation of this for EM as well. And hopefully I will now be available to take questions, and hopefully I've also been taking them via text chat during the course of the talk as well.
Thanks for that, Kevin.